Have you ever wanted to track your sleep during the night with a next-gen wearable, but found that it interrupted your sleep? That's what's happening to the four people that you see right here. The bulky wearable presses against their wrist and keeps them up at night. But what can we do to solve this?
Introducing the PillowCheck, a new innovative sensing platform that integrates with your pillow to provide unobtrusive ambient sleep sensing without interfering with your normal routine. PillowCheck differs from typical ambient sleep sensing platforms like smart matches in that it is easy to set up in addition to being low cost. PillowCheck uses a futuristic capacitive sensing to gauge your sleep quality and can provide a sleep score, just like all the other bulkier and obtrusive solutions.
But what is this capacitive sensing technology? For some quick background, a capacitor consists of two parallel plates with a dielectric material in between them. We can calculate a value called the capacitance, which is dependent on the dielectric, the area of the plates, and the distance between them. We can then associate the capacitance with a pressure or load. We measure capacitance on a microcontroller by connecting the sensing node with an LC tank and measuring the frequency of the signal's oscillation. We can then use the equation F equals 1 over 2 pi times square root of LC to calculate capacitance. In our case, we are using conductive textiles to create unobtrusive capacitors on the surface of the pillow and then map the load distribution on the pillow over time.
We can associate this data with sleep quality by considering several metrics. For starters, we know that deep sleep is characterized by minimal movement and slow breathing, whereas REM fosters micromovements. We can therefore classify these stages and track nightly cycles. From there, if the sensors detect movements during deep sleep periods, for example, it will count against one sleep score. Additionally, our system will detect and count conscious movements, like raising your head, against one sleep score. To begin, we created a 4x4 array of copper tape, which will serve as the capacitor plates, separated by a layer of foam tape to act as a dielectric. The four strips on one side overlap with the other side at 16 distinct grid points, each functioning as a capacitor.
To measure the capacitance, we connect the leads from the rows and columns of our sensing array to a multiplexer, and then send those inputs into a capacitive sensing chip. From there, we can simply use I2C communication protocol to get the capacitance from this chip onto our microcontroller and then send that where we need it to go. When we send this data to our computer, we can create a heat map GUI, which shows the location and intensity of pressure over time.
Moving on to results and discussion. Crucially, we found that a malleable dielectric and backing are essential to develop a pressure gradient. Without them, the system acts merely as a binary touch sensor. While our first version hard-base proved the circuit logic, we needed comfort. We iterated through soft cloth and feather pillows. We found that the third version, feather pillows, caused unpredictable capacitance changes due to shifting materials. Ultimately, we chose the fourth version, memory foam. It reduces plasticity and provides a consistent, repeatable dielectric layer, which is crucial for accurate data collection. A major challenge was sensitivity. We tested various conductive strip widths. Our experiments confirmed that wider conductive paths significantly enhance sensitivity. Following Ohm's law, the wider surface area reduced the resistance and provided the clearest signal. This optimization was key to detecting subtle head movements through the pillowcase.
The pipeline starts with data collecting. We employ the FDC2214 chip, which utilizes an LC oscillation circuit to detect minute capacitance changes. To manage our sensor matrix, we integrated two analog Macs to rapidly scan through each node sequentially. Once digitized, the signal is transmitted to Arduino unit via I2C protocol for signal cleaning. First, hysteresis is used to determine the state. It prevents the signal from flickering when pressure is near the threshold. Second, when the sensor is at idle, we use an adaptive baseline with exponential drop-off controlled by a tunable alpha smoothing factor, acting as a low-pass filter. This automatically adjusts the baseline in real time to reject environmental drift caused by temperature or humidity changes. When the sensor is sensing, it will freeze the baseline and calculate the delta. As for processing, we perform dynamic calibration via normalization. This scales every single node's output to a uniform standard between 0 and 1. This ensures that a light touch registers consistently across the entire matrix. Finally, we map the normalized values to a heat map. The system operates at a 1.2 Hz refresh rate to maintain signal integrity and prevent channel interference from the FDC sensing chip.
Here is our final working prototype using a 4x4 sensor array on a memory foam pillow. As you can see, the heat map updates in real time as pressure is applied. We optimized the system to a 1.2 Hz refresh rate to maintain signal integrity from the FDC chip without deterioration. PillowSense successfully demonstrates how capacitive sensing can be embedded into everyday objects for unobtrusive sleep monitoring.